We are now recording. Behave yourselves, people. All right, and my next question for you guys is, does everybody on the call know how calibration frames work, or would anyone like a few slides on how darks and flats and bias work first? And I'm going to unmute.
I definitely wouldn't mind an explanation of blacks and bias. I really don't get that.
Okay, cool. So we will do that. So where should we start? Yeah, let's actually start with that then. So let me pull up my slides here, and we'll do the screen sharing thing, if I can figure it out. All right, let's talk about calibration frames. So this is the part that I'm not going to totally step through throughout this exercise, because I provided you with some pre-integrated dark frames and bias frames as part of the data set that we're playing with. But just a background of what they are. Go there. So the first calibration frame is called a dark frame. And the purpose of a dark frame is to address what we call dark current. And this can be basically defects on the sensor. So this is what a dark frame looks like after it's been integrated. And you can see this kind of a speckly look there. I'm not sure if it's coming through on Zoom or not, but every sensor has, some defective pixels or some pixels that are more sensitive than others. And by taking this dark frame, we can capture where those differences are and subtract that out from our final images to calibrate them and make sure that those changes on those specific pixels on the sensor get calibrated out of our image, so we don't end up with this speckly image when we're done, right? And if you look closely, again, I'm not sure if you can see that, but there's also some bad columns on here too. So depending on what kind of a sensor you might have entire columns that are a little bit dimmer than others or a little bit brighter than others, and a dark frame can account for that as well. You'll also see that there's things called like amp glow. So kind of the edges are a little bit brighter than the center, for example. Sometimes, the cooler has that effect on the chip, and this also lets you calibrate that effect out as well. So the thing with dark frames, the good thing is that you can build up sort of a library of these ahead of time and just keep them around for like a year, which is what I do. So, you pick a day and you just run this automated thing. You put the cap on your lens cap on your telescope, and you just like kick off about 20 frames or so for every combination of binning and temperature that you might be using in the future, and exposure time. So you have to make sure that you match up the temperature, the binning, and the exposure time for your dark frames for them to calibrate out properly, because the longer you expose, the more prominent those hot pixels are going to get. So if you have a CCD sensor, you can get away with scaling them. So it is possible to use a dark frame for one exposure with a light frame from a different exposure. That's okay, but it's always better to have one that matches up if you can. If you're on CMOS, though, you do need to have that exact match between the dark frame's exposure and the exposure of the image that you're calibrating. Okay, so that's one fundamental difference with CMOS. But once you've actually done this, you can just build up a library ahead of time and either throw the cover on your telescope, or if your camera has a shutter, make sure the shutter's on, or just go outside and do it when it's pitch black out. And take about 20 or so for every combination of binning and temperature and exposure time that you might need, and integrate them all together using whatever your choice of integration software you have. And I'm going to pop out the chat here. Yes, I am recording, Mark, I think. I hope. Maybe. There should be a notice saying that we're recording, actually.
Yeah, it's recording.
Okay, cool. Yep. All right, so before I move on, any questions about dark frames and what they're all about? All right, moving on. Now, the next thing we have are what we call bias frames, and this addresses what we call fixed pattern noise. And the idea here is that we take a bunch of exposures with no exposure length at all. So we're just sort of capturing the read noise, the noise that's inherent to the camera itself, irrespective of your exposure time. And since they have no exposure time, or a very short one, you can take a whole lot of them really easily. So it's common to take like 100 frames, basically with no exposure length at all. And since you're not exposing at all, it really doesn't matter, but it's a good practice to put the cap on anyway. And the thing with bias frames, though, is that they're mostly useful for CCD cameras. If you have a CMOS camera, you're going to get something that looks like that, most likely, where you have this like really horrible amp glow coming out there from the side. And that kind of makes your bias frames kind of worthless. So if you're using CMOS, you're better off using what we call flat darks. So make sure that you have dark frames that match the exposure of your flat frames. And we're going to use a different calibration technique in the case of CMOS, where we're just not going to use bias frames. And finally, we have flat frames. And flat frames will look something like that for me anyway, where I have terrible vignetting. And you can see kind of a dust bunny there too as well. So that donut shape there in the corner is just the reflection of a dust particle. Hey, someone's got their TV going there. If you could mute yourself. Or I could forcibly mute everybody. All right, whoever it was, turn their TV down. Thank you, I think. So yeah, the idea here is to sort of capture the vignetting and like the difference in light exposure from your telescope. So it's pretty common for the center of your image to be brighter than the outer edges of the image. And it can also calibrate out these dust artifacts that's either on your camera or on your lens or whatever it might be. So you don't want to have these big donuts in your final image if you can help it, obviously. A flat frame will help you get rid of that. So when you're taking a flat frame, you want to make sure, again, you match the binning and temperature and whatever filter you're using, because those dust bunnies might be on your filter, you know, if you're using different filters on a filter wheel. And make sure the camera rotation matches exactly the rotation that you used when you were taking the images that you're calibrating. So this makes flat frames kind of a pain, because if you take your camera off and put it back on, you're going to need a new set of flat frames no matter what. And, you know, even from one night to the next, there might be differences in, you know, how your dew shield is positioned that might affect how your flat frame works. So generally speaking, you want to take a set of flat frames every observing session that you have, every imaging session that you have. You can get away with recycling flat frames across, you know, a couple of nights if you didn't move the camera at all. I've done that, you know, if I had like a problem with them and gotten away with it. But best practice is to always take a set of flat frames every time you do image. So you want to expose that for however long it takes to get about a third of the way up on the histogram, about 25,000 ADU if you have, you know, a 16-bit camera. You want to aim for taking about 20 of them per, you know, filter temperature combination. But, you know, if you're cheating by taking dawn or dusk flats, you might have to make do with less because the sun might rise too quickly for you. What do I mean by dawn flats? So there are a couple of ways to generate these flat frames. Actually, there's several ways. One is to get an E-luminance flat panel kind of a thing and just like stick that on top of your telescope. And it's just like a really uniform field of light that you can buy and just stick on the end of your telescope and do it that way. That way you can take a flat frame anywhere, anytime. It's nice because you can take your flat frames ahead of time before you start imaging or after the fact, whatever you want. Another technique is sky flats. And the idea there is you can just point your telescope at an empty part of the sky, hopefully straight up-ish if there's no clouds. And, you know, if you do that at the right time of dawn or dusk, the exposure will work out. And that's usually how I do it. I have some automated software where at the end of my imaging run, it will wait for the sun to rise and just start taking flat frames automatically. That works great if there's no clouds. If there are clouds, then I'll have to go back and actually use my flat panel instead. Another way is the t-shirt method. So, you know, you can just throw a white t-shirt and, you know, kind of like rubber band it around your telescope and point that at the sky and get your flats that way as well. That's another technique. But you will always need flats. All right, Mauricio, I hope that helped. If you have any questions, now is the time.
Yeah, that helped a lot. Thank you. I get a really bad vignetting when I image, and the flat. I haven't been doing flats, so that I think that pretty much is going to help me out a lot. And I also didn't understand what bias frames were, but I have like a regular camera, so I don't think that would help me since the glare problem.
Yeah. I mean, bias tends to be the least important of them, honestly.
Yeah. The flats, that was super informative.
Yeah, if you do anything, do flats. There are even some cameras where you can get away with not doing darks. Like I had an old ASI 414EX that had such low noise, read noise, that I could get away with not using darks at all. So, you know, some cameras you don't even need that, but you will always need a flat frame. That's the most important one.
Because I've only been doing darks, so it's really good to know.
Mm-hmm. Cool. All right. Hey, somebody learned something. Woohoo.
Yep.
All righty. So with that, let's go into PixInsight. And I will share my screen again. All right, so if you are following along, now is the time to start PixInsight. And again, don't be shy about yelling out, "Wait up, Frank, I'm not ready for you yet." If I'm going too fast, just slow me down. That's, you know, I'm here to help. All right, so let's start off here. Hopefully you had a chance to download the extra scripts and process icons that I provided in the meeting invite. If not, there'll be a few things you'll have trouble with, but one of those things was my process icon set. So if you did download that, step one is go to the process menu and go to process icons and say load process icons and select Frank's workflow. And what this does is give you a bunch of process icons that are kind of like my cheat sheet of settings that I commonly use when I'm processing images. So each one of these represents basically a set of settings for a specific process in PixInsight. So for example, if you look at, I don't know, TGVD, that's actually a noise reduction step that we do toward the end. And it's preloaded with all my favorite settings there for, you know, how that's actually applied to the image. So it's just a way for me to save my settings from run to run and not have to type them in every time. So it's a time saver, and it's a way for you to like quickly get at sort of some of my secret recipes, as it were. So with that, the first thing we want to do whenever you're going to be processing a night's worth of data is to evaluate that data and make sure that you're throwing out any bad frames, because your final image is only going to be as good as the frames that you put in. Garbage in, garbage out. Now, we are going to be using some techniques to automatically weight those frames based on how good they are, so they don't have to be perfect, but if you throw in a really terrible frame, there's no making up for that. So we want to make sure that we take a look at those images and evaluate them somehow. Now, there are automated ways of doing this. There's sort of a subframe selectors process you can run that will automate this to some extent, but frankly, I don't trust it. There's nothing better than your eyeball, in my opinion. So let's use our eyeball to evaluate these subframes. So to do that, we're going to go to the process menu and go to all processes and select blink. And what this does is let you load up a whole bunch of subframes and compare them visually very quickly. So to do that, let's click on the folder icon here. You're going to find that PixInsight's user interface is really, really, really strange and counterintuitive. It's like nothing you've seen before, but the best way to learn it is just to watch somebody working with it. So I hope you'll pick some of that up as we go here. It's completely strange. But anyway, in this case, you want to click on the folder icon, and we're going to navigate to that sample data that hopefully you've downloaded already. So for me, that's in here. And to make things more fun, I'm actually splitting our data up over 2 nights. So I actually imaged the Pac-Man nebula over October 5th and October 21st of 2019 here. So this makes things a little bit complicated because we're going to have 2 different sets of flat frames from those 2 nights. So we have to calibrate these 2 nights independently. But we'll get there. We're not there yet. First, though, we want to make sure that our frames look good. So let's start with the October 5th data. We'll open that up. And I'm going to just select everything in here, Control A, and hold down Control and select calibration files because I don't want to select that folder. I just want these fit files. So basically, we have a couple of hydrogen alpha exposures in here, a bunch of oxygen 3, and a whole bunch of sulfur 2. Now, again, we're doing narrowband imaging here. Excuse me. So I'm like imaging this through 3 different narrowband filters. That's one of my main techniques for fighting light pollution here in suburbia. So hydrogen alpha in particular is extremely resistant to light pollution. So if you're wondering how the heck I get images as good as I can get from Bortle 8 skies, that's trick number 1. So let's hit open here. And first thing we're going to do is click this magic icon here. And if you mouse over it, you'll see it tells you what it does. It applies an automatic histogram transformation to all images. Now, when you're taking deep sky photographs, you know, in reality, these things are so dim that if you just look at them as raw data, they're just going to look like black with a few stars in it. So we need to stretch the data to see what's actually in it. And one of the main things that's powerful about PixInsight is that it has the ability to stretch these images while you're still working with them in that linear space and kind of see what you're doing, you know? So it has ways of cheating and like looking at your data as though it were stretched without actually stretching it first. This gives us the advantage of being able to apply a lot of processing before we stretch that image out to the full range of visual data that we'll end up with. And that actually is beneficial for some operations. But anyway, by pressing this, we're going to apply a automatic stretch to every one of these images so that they all look like something reasonable. So I'm just going to click on that first one. And you can see that there's an image of the Pac-Man nebula there in hydrogen alpha. And it looks pretty good. So let's just hit the down arrow button here and kind of flip through them all here. And we're just looking for ones that absolutely suck. So those look okay. Now, for oxygen and sulfur, you're going to have a much dimmer signal. So this actually looks reasonable to me. So this is all pretty good oxygen data. Still just kind of using the down arrow. Now we're into the sulfur data. And after I do a meridian flip, by the way, it's going to flip these images as well, but we'll correct for that later. Don't worry. You can see there the meridian flip happened. We went from east to west there, so it actually flipped the image, but PixInsight can handle that when we align everything. So far, these all look pretty good. And if you want to be sure, you can kind of zoom in a little bit. So if you mouse over that screen and kind of use your mouse wheel, you can zoom in that way and kind of get a sense of how good the stars are. So I've always been battling tracking issues for some reason, but you want to make sure that you don't have anything where the tracking is so bad that your stars look like lines instead of, at least a football. William asks, what do you look for in a bad individual image? Well, we'll have an example in the next night's image. But what I'm looking for right now are really bad, clouds coming through, for example, planes flying through. That's going to be a hard thing to get rid of. And for really bad tracking where the stars are just stretched out completely. So by zooming in, I can evaluate those star shapes a little bit better. Let's just take a look here. You can see, definitely some are better than others, but they all look reasonable. Oh, it looks like a little meteor went through there or something. That's not a big deal. We can calibrate that out. There's another one. Huh. Maybe a cosmic ray. That one's kind of curved. Weird. So, the stars aren't awesome, but they're good enough, right? So as long as they don't look like lines, I'm happy. So let's take a look at the second night's worth of data here. So I'm going to close these out by using this little icon here, close all images, the third one over. Boom. And now I'm going to open up the data from that second night. So that was 1021. And same thing, I'm going to Control A to select all of it. Select the calibration files to deselect that and open those all up. And let's see what we have here. All right, again, we'll apply a stretch by clicking that icon on the top. And let's see what we got. So I selected that first one. I'm just going to use the down arrow to go through them. Oop, looks good, looks good, looks good, looks good, looks good. What the heck happened there? So two things, one, we have this like terrible vignetting going on in the corner here that we didn't see anywhere else. And if I end up including this image in my stack, I'm going to have like a really bad artifact there that's going to be really hard to get rid of. And that's going to require me to basically crop my image to get rid of that. But I don't want to crop all that space. So if this is the only frame where I'm seeing that, or there aren't too many, I might just want to throw this out. Also, the nebula itself looks kind of dim, so I'm not really sure what went on here. I'm kind of suspecting that maybe my telescope got a little bit too close to a street light here, and it's washing things out and maybe casting some weird shadows from my dew shield. So this is potentially a bad frame. Let's keep going. Same deal there. It had all the other problems, plus an airplane flew through. Now, now, if this were a satellite, I'd be okay with it. Like you can actually calibrate out satellite trails pretty easily. But, a big, thick monster like this, that's tough to get rid of. I mean, if you zoom in, it's just terrible. So that's got to go. Like that's hard. There are ways to actually get rid of that in processing, but I don't feel like dealing with it. So those two seem bad. Let's see what the rest look like. Oop, that one looks good. That's more like it. We've got an O3 frame here and some more sulfurs. So it's just those two that I don't really like. So let's get rid of them. So to get rid of them, you just select it. And I'm going to just hit Shift Select to select those two bad frames. And the blink UI, again, is counterintuitive. So to get rid of it, you would think you could just hit delete and it would go away. But no, that's not how it works. Also, it's not the case that whatever's selected is what goes away. That's not how it works either. But what is selected and actually made orange, you can just click on this move icon here, that fifth one over from the left, and we can move that to some place where we aren't going to notice it anymore. So let's go to our Pac-Man data folder and make a new folder called bad frames or something. And I'm going to select that folder and click select folder. And even though it doesn't show you in this dialog, it moved those two files into that bad frames folder. So now when I go to select everything to integrate, those two frames will not be included at all. I threw them away. All right. So that makes me happy. The frames that I'm left with are good, so we can move forward. All right. Before I move on, we got some questions. So Eric asks, when deleting blemishes and intruders, does the program know to fill that void in the image with matching background? Yes. The way it works is through a pixel rejection algorithm when it does the stacking. So, if it does see an outlier where you have a streak in one image and not in the rest of the ones in the stack, it will just not include that pixel in the average. So basically it uses the remaining frames to figure out what should be in that spot where that streak would be, if that makes sense. But it works really well. The problem comes in where, we have these sort of like fuzzy lines, like an airplane trail, where it's not really clear if it's really signal or not to the algorithm. But. All right. Any questions before we move on to actually calibrating this data? Everybody caught up? All right, moving on. So it used to be that calibrating data in PixInsight was a very long and tedious process, but it's been made a lot easier lately through the new weighted batch pre-processing script that just came in this year. So I'm going to go to the script menu, go to batch processing, and select weighted batch pre-processing. Now, if you take all of your data in the same night and you have the same set of calibration files for everything, the same flats, this is super easy. You just add in your bias frames and your dark frames and your flat frames and your light frames, and you press go and you're pretty much done. And it gives you a stacked image. It's super, super, super easy. Way, way easier than it used to be in PixInsight. But for us, it's going to be a little bit more complicated because we did take data over 2 different nights and we have 2 different sets of flats. So our overall strategy here is going to be to calibrate these 2 nights of data independently. So I'm only going to calibrate as a first pass for these 2 nights of data, and then I'll come back and integrate them all together with a third run of this script. So let's see how that works. So my first task is to calibrate the October 5th data. So let's click on the bias tab here, see what we got, and we'll just click on the Add Bias button. And if we go to our sample data, there is a darks bias folder included, and you'll see here a super bias. There are a couple of different flavors of bias frames. If you just integrate them all together ahead of time, I have a master bias, but there's also something in PixInsight that will generate what's called a super bias, which can be a little bit better sometimes. So we'll use that one. We're going to add our dark frames. So which dark frames do I need? So there are basically 3 things I need to calibrate here. One is going to be my flat frames, and those are typically on the order of, 10, 20, 30-second exposures. I need to then calibrate my actual light frames, the actual sub-exposures that I took throughout the night as well. And I know that's a combination of 5-minute and 10-minute data. So I'm going to select my 60-second darks, my 300-second darks, and my 600-second darks, because I know that will cover pretty much everything. Now, again, because I'm using a CCD camera, that 60-second dark can be scaled down to match those flat frames that are actually lower exposures. If you're using a CMOS camera, you will need to make sure you have darks that pretty much match exactly the exposure time you used for those flat frames. I can just get away with this because I'm using a CCD. So let's hit open and add those dark frames in. And we're going to add in our flats. So click on Add Flats. Go up to Pac-Man Data and go to the 2019-1005 folder. And in there, we have calibration files. And that's where the flat frames are. And again, these are Dawn flats, where I just told my image acquisition software to point at the zenith and take 6 frames each under each filter as the sun came up and automatically figure out the right exposure length for me. So, really you would want to use Blink to actually make sure these flats are all good, because if you have clouds coming through, that can mess it up. But I already did that. So let's Control A for everything in here and click on Open. And there's all of our flat frames. All right. And lastly, but certainly not least, are our light frames. Those are the actual exposures of the Pac-Man nebula itself. So we'll click on Add Lights. Click back up to the 2019-1005 data and select everything except for the calibration file. So I'm going to Control click on that to deselect that folder. And we'll go ahead and hit Open and add in our light frames. So you can see we have, it organizes things nicely for us. We have 2 300-second hydrogen alpha exposures, a bunch of 300-second oxygen 3s, and a bunch of 300-second sulfur 2 exposures. All right, so let's double check everything here. We have our super bias. Now, this is actually pre-integrated, right? So this is what we call a master bias frame. I didn't throw in 100 different individual bias frames. I could have, though. It would deal with that if you did. But since this has already been integrated, it's kind of like part of my library of calibration frames. I'm going to click on Use Master Bias to make sure that it knows that this is already integrated. Looking at the darks. All right, again, we have the ones that we expect here, the 60, 300, and 600 ones. We don't actually need the 600 ones for this data. That's going to be for the next night, but hey, it doesn't hurt to have it in there. Again, these are pre-integrated. I did not just throw in my loose sub-exposures for these dark frames, although I could have, but because I didn't, again, I'm going to click on Use Master Dark here on the global options. Okay. Flat frames. These are not pre-integrated. These are my actual individual flat frames that have not been integrated already. So I'm not going to click on Use Master Flat. That means that PixInsight will go ahead and calibrate every one of those frames using my dark files, and it will then integrate them together to create a master flat for these three filters automatically. All right. Next thing we have to do is set an output directory. So click on the little folder icon next to Output Directory. And we got to put it somewhere. So pick some place on your hard drive that has a lot of space. I'm just going to make a new one called Pac-Man in my documents. Oh, I already have a Pac-Man. Let's call it Pac-Man CFAS. Click into that and say Select Folder. So that's where the output's going to go. And finally, let's click on the Lights tab here. And we're going to click on the Calibrate Only button here, because again, we're going to do this in a few different passes because I have data from 2 different nights. So first, I'm going to just calibrate that night's data. Then I'm going to calibrate the second night's data. Then I'll come back and integrate it all together. So let's click on Calibrate Only. And that grays out a bunch of integration options that I'm not going to worry about right now. And everything else should be okay with the default values because we're just doing calibration. It's pretty straightforward. The only thing you really want to check is those Use Master Bias Dark Flat settings.
Frank, can I ask a quick question?
Absolutely.
Can you go back to the Flats tab?
Mm-hmm. There you go.
Should there be a check mark and calibrate with flat darks? Or what's that box for?
Calibrate flat dark. Oh, that one. Yeah. So flat, if you check that, that means that the script is going to make sure that you have matching darks for every flat that you have. So if you're using a CMOS camera, that might be something you'd want to do. That's going to make sure that if you have a 6.27 second exposure for a flat frame, you have given it a 6.27 second exposure for a dark frame to match it.
Right.
But by not checking that,
I thought you did that. I thought you created flat darks.
I did not. I did not. So I just have the only darks that I have in there are 60 seconds, 300, and 600.
Okay.
So by not selecting calibrate with flat darks, it's just going to take that 60-second dark and scale it down linearly to match those exposure times for the flats.
Okay.
All right.
I thought I heard that you had that you were creating flat darks.
Nope. Nope.
Okay.
I would only do that
but
with
if
CMOS.
you do, you would check that box if you're
correct
creating darks the same length as your flats.
Yep, that's right. Yep. So, you know, bottom line, if you're using CCD, you probably don't want to check that. If you're using CMOS, you probably do want to check that. All right. All right. So I think we're ready to start calibrating this puppy. So looks good to me. Let's go ahead and hit run and see what happens. Oop. So it's going to give me some warning. And this is exactly what we were just talking about. It's saying, hey, we're going to take your 60-second dark and scale it down to match your different flat exposures, which are all over the map here. But again, because I'm using a CCD camera, I can get away with that. So we're going to say continue. And off it goes. So right now it's calibrating all of my Pac-Man subframes for that night using the darks and biases and flat frames that I gave it. So the first thing it's going to do is calibrate those flat frame sub-exposures. After it's done with that, it will integrate the flat frames. So I have a master flat for each filter. And finally, it will apply that master flat, the master dark, and the master bias to every sub-exposure for that night. So this will take a couple of minutes. Hopefully not much longer for anyone else.
There is growing concern today that college students heading home for Thanksgiving will spread COVID-19 across the...
Someone's watching the news. Bad. Don't watch the news. It's not good for you. All right. All right, so that finished. And if we look at the folder where we put everything, you can see that it created a bunch of subfolders here. So we have a calibrated folder, and under flats, we see our calibrated flat frames, and under lights, we see our fully calibrated sub-exposures. So yay. There's also a logs folder if you want to like see what happened, and a master folder that at this point contains those master flats that we created. So, excuse me, that might come in handy later. All right, so now we have to do it again for our other night's worth of data. So all I'm going to do here is on the lights, select clear, and go to add lights. And we're going to go into that 1021 nights worth of data. Note that those bad frames have been moved out by that blink process already. So I'm just going to select the remaining ones. And little thing here, note that it automatically checked use master flat here behind my back because it wants to reuse those flat frames that I just created, but I don't want to because I actually have a new set of flats for that night. So let's go ahead and on the flats tab, clear out those flats. And we're going to add in the flats that match that night's data. So under calibration files, I have the flats from 1021. Just going to Control A to select all of them and click open. And now I have a new set of flats, and I'm going to unselect use master flat again because I wanted to recreate the master flat based on these new flat files that I'm giving it. All right. The bias, however, is the same. The darks are the same. New set of flats, new set of lights. And note that these are 600 seconds. So for whatever reason, I decided to go for 10-minute exposures that night. This is usually not a good idea, guys. Like, you don't want to mix and match exposure times if you can help it, but I was just trying to push the envelope, I guess, whatever. It works out in the end, but it does make things a little bit more complicated. So let's go ahead and hit run again. Make sure the calibrate only is still checked, and that all looks correct. And let's go ahead and kick it off. We have the same set of warnings about scaling our darks down to the flats, but I have a CCD camera, so I can get away with that. Continue, and off it goes. So calibrating and integrating our flat frames, and then it will start calibrating the actual sub-exposures. Which
its legacy. Trump is reportedly doing what he can to block the Biden team.
I found it. All right, so you can see it was integrating those flat frames, and what's it doing now? Now it's actually calibrating the actual sub-exposures. Should be done soon. All right, we're done. Does anyone need me to pause while you catch up? Is everyone good? If you're screaming, wait, Frank, I can't hear you because you're muted. All right. All right, then, moving on. So we have our calibrated data, and now we just need to integrate it all together and actually do the stacking. And, you know, at that point, we can start to have fun. Things get more interesting after this, I promise. We get pretty pictures next. So to actually do that integration, I'm going to uncheck calibrate only because I don't want to calibrate at all. I just want to integrate. So I'm actually going to go to my bias frames and remove my bias frame. I'm going to go to my darks. I'm going to remove the darks. I'm going to go to flats. I'm going to remove my flats because I've already calibrated everything. I don't want to calibrate it a second time. That would be terrible. And I'm going to go to lights, clear that as well. And I'm going to add in lights that are those calibrated data files. All right. So if we go to wherever we saved everything, so for me, that was the Pac-Man CFAS folder, and we go to the calibrated folder and we go to light. These are all the final calibrated light frames there. Eric asks, if you happen to hit the keyboard while it's compiling and such, will it interrupt the process? No, not unless you hit like controls. I think you have to actually hit the abort button there for it to actually get messed up. So it's usually pretty robust. So I'm going to Control A to select all of those calibrated light frames. Make sure you're in the right folder here. All right, so I'm kind of like tricking this script out. I'm saying, I don't want you to calibrate this stuff again, so I'm just not going to give you any calibration frames, so you can't do any harm. And I'm going to give you lights that have already been calibrated. All right, so a little bit of a trick for handling data across multiple nights that have multiple flats. Since I don't have any bias darks or flats, it doesn't really matter what I set here, but I'm going to uncheck them anyway. Output directory stays the same. The one thing you do want to check, however, is the exposure tolerance. Now, by default, I think this is only like 5 seconds or something. And if you do that, it's going to split up those hydrogen alpha frames into 600-second exposures and 300-second exposures. And the same for oxygen and sulfur. But I don't want to have separate integrated stacks for the 600 seconds and 300 seconds. I want them to all be integrated together. So to trick it out, I need to increase the exposure tolerance to at least 300 seconds so that it groups together those 5-minute and 10-minute exposures into a single stack. And you might say, Frank, is that really a legitimate thing to do? I can get away with it because it's weighted batch pre-processing. It's going to actually evaluate the signal to noise ratio in each one of these subframes and weight each subframe appropriately as it stacks them together. So it will automatically say, hey, these 10-minute exposures are way better than these 5-minute exposures. I'm going to give them, twice as much weight or whatever it is. So it kind of works out. But yeah, again, it's best practice not to do that. Just take your sub exposures at the same length if you can.
I don't see where that, there it is.
Right here,
Okay.
exposure tolerance.
Yep.
It's under the calibrate only box. And the other thing that we want to...
lights. Yep.
Okay.
Okay.
With me? Cool.
Yep.
Other thing we want to check is the subframe weighting. So you want to click on the weighting parameters button here, and you see you have a few presets here to choose from. You have nebula, galaxy, and cluster, and that's exactly what it sounds like. We are integrating a nebula here. So what this is doing is kind of like figuring out the formula for how it weights each subframe. So it's giving a certain amount of weight to, how tight are your stars? How good's your focus? How round are your stars? What's your signal to noise ratio? And depending on what kind of an image you're trying to make, you might want to make different trade-offs there. So for example, for a globular cluster, you really want pinpoint stars. That's what the most important thing is. But for a nebula, I care mostly about signal to noise ratio because they're these large, spread out objects. So we're going to go ahead and just use this preset for nebula there. And we can click on the X there to get rid of that option there. You might want to double check the check marks here. We do want to do image registration. We do want to auto detect the best reference frame. And we want to apply image integration. So that's the whole point. At this point, we're integrating the calibrated frames. And I think that's it. Let's go ahead and hit run. And it's going to complain very loudly. It's going to say, oh my God, you have no calibration frames at all. What's wrong with you? Yeah, I know. That's because I don't want you to calibrate it. So live with it, PixInsight. Continue. Off it goes. So now you can see that it's actually evaluating each subframe and measuring the FWHM, which is basically how tight your focus is, the eccentricity of your stars, and the signal to noise ratio. And it's going to go back in another pass and use those metrics to figure out a weight for each subframe. So we'll just let it do its thing. And it's also going to register them while it's at it, make sure everything is star aligned. And when we're done, we should just end up with a stack for hydrogen alpha, oxygen 3, and sulfur 2. So not that hard. And again, if you had all of your data taken on one night and you just had one set of calibration files to deal with, we would have been done a half an hour ago, guys. The weighted batch pre-processing script is super easy to use. If you just throw in a bunch of biases and darks and flats and light frames and say go, and that's pretty much all you have to do. So, once you use it once or twice, it's actually, in my opinion, even easier than some of the programs like Deep Sky Stacker or Nebulosity or something like that. That script has made it a lot more accessible. And it's using much more sophisticated algorithms under the hood too, which is even better. So we're just going to wait for this to finish. Somebody hummed the Jeopardy theme. Poor Alex Trebek. My wife and I were debating if they should even continue doing Jeopardy at this point. I say no. Off it goes. Basically, it's rewriting things with the metadata for those weights at that point. And now it's doing the registration step, where it's actually aligning everything based on their star positions. And it's doing the integration. It's going pretty quickly, actually. Now, how long this takes very much depends on how good your CPU is. So y'all just let me know when you're done.
I still hear someone's TV.
I'm guessing it's Leonard. Yep, guilty. Sorry if I used my magic administrator powers to mute you. All right, so mine is done. And if anyone's still going, let me know. I'll wait for you. Make sure you unmute yourself, though. All right, moving on. So we're done with the script. I'm going to hit exit. Yes, I really want to exit. And let's see what we got. File open. And here we are again in the master, directory here. These are our final integrated flat frames from that previous night's worth of data and our integrated light frames. Let's select all and open. Let's see what we got. Oh no, it's terrible. It's nothing but blackness with a few dots. Well, of course, this is still in the linear space, so we haven't actually stretched this image out to fill out the color space that we can see, but the image is hidden in there. We just got to pull it out. And what's beautiful is that that's pretty easy to do with PixInsight. So if you double click on the STF icon here, that's the screen transfer function. This is a very handy tool for automatically applying a stretch visually to what you're looking at in PixInsight without actually stretching the data itself. So this allows us to work with our data while it's still in linear space and apply some transforms to it and work with it before we actually stretch it out, which has some advantages. The way to use it, just click on this little radioactive icon here. Again, PixInsight's UI makes no sense at all. Click the radioactive icon. That's what you do. And there is revealed our sulfur 2 data. It's pretty good. You know, sulfur 2 is usually pretty faint signal, but we're definitely seeing something there. So that's encouraging. While I'm here, I'm going to rename it to something more useful. So if I hover over this left tab here, for lack of a better word, it has this default name, Master Light Binning 1 Filter S2 Xpine 600 Integration. That's kind of hard to type or say. So I'm going to double click on that and change its name to S2. So now I can refer to this as S2 in my scripts, which is going to be a whole lot easier. We'll do the same thing for O3. Again, hit the radioactive icon so we can see what's actually in there. And I'm going to double click on the left tab there and rename this to O3. And we'll go to hydrogen alpha, which I hope looks beautiful. That's usually your best data. Oh yeah, I'm liking that. Double click on that identifier and we'll rename that to HA. Alrighty, and then we also have our master flats here. Again, in a perfect world, you'd have the same set of flats for all the data, but we don't have that luxury, but hey, that's cool. We'll live with it. Just to eyeball it, make sure they look reasonable. Can apply a stretch to that as well. Hey, it looks like a flat frame. How about that? Now, if you want to minimize this thing so you don't have to look at it and clutter things up, you can click on this icon here to kind of like roll that window up and just kind of tuck it away somewhere. Same thing for that flat. We are actually going to be using these flats in a moment, so I don't want to actually close them, but I just don't want to look at them. All right. Now, the next thing we're going to do is our first round of noise reduction. And it's usually better to do noise reduction in the linear space if you can. So if we zoom in, you can see our hydrogen data looks pretty darn clean, actually. But, you know, out here in interstellar space, there's a fair amount of noise going on. But when you get into like the S2 data, it can get ugly. So, or O3 even, because this tends to be more susceptible to light pollution. You can see it's kind of grainy. Yeah, so let's see if we can cut down that noise a little bit. So kind of my favorite noise tool these days is something called Mirror Denoise. If you go to Script, go to Noise Reduction, and say Mirror Denoise. Now, you don't have to do this. You can skip this step if you want to, but I find it helpful. It's a little bit tricky, though, because you have to know the properties of your camera here for it to work properly. So if you don't know these numbers off the top of your head, you can go and Google them real quick if you want to, or you can just not do it and watch me and do it later and take my word for it that it does something. But you
If
need
I
to know.
could make a comment here, though, this Mirror denoise only works good on the narrowband and CCD stuff.
I'm not sure that's entirely true. I've definitely used it on galaxies and broadband images too. It may be that it's better for CCDs than CMOS, though. I don't know. But a lot of PixInsight is just kind of experimentation and seeing what works best for your equipment and the images that you have. So your mileage may vary. But for me, it's actually pretty effective. So I had to go look up the gain of my camera. And if you mouse over this, it will tell you more about it. So if you can go look up your E minus over DN value for your camera, for me, it's 0.410 for my Attic 383L plus. Gaussian noise is probably something you'll have to do a little bit of calculation for. So if you do know the gain and you also know your read noise, you can figure out your Gaussian noise here, just following what it tells you here. So if you take the read noise value in electron volts and divide it by the gain, that gives you the value that you want to put here. So for my camera, that's going to be 17. And I have no offset because it's a CCD camera. It doesn't have one. Now, the main thing here is you want to make sure that use image metadata is checked. That will automatically populate how many subframes you have and what you're trying to denoise. And the variance scale is going to apply how strongly the effect is applied. Now, I have that cut down to 0.5 because if you set that too high, you're going to end up with these weird checkerboard patterns, artifacts in your background. So you want to have kind of a light touch. I mean, that's really true of pretty much all processing, right? You don't want to be too heavy-handed in your processing or things start to look weird and cartoony. I could probably get away with a little bit more. Let's set to 0.6 just for fun. And what you want to do is select the image that you want to denoise. For me, that's the one that I called HA. And you want to select the matching master flat for it. So for me, I'm going to use this one. Again, yes, that is using a flat from 1 nights of data and applying it to a stack from 2 nights of data. It doesn't have to be perfect. We can actually get away with that. So I'm going to click the denoise button and let it do its thing. Again, your values here will be different depending on your camera. There's also, if you go to the scripts noise menu there's a script that will actually try to calculate those values if you feed it your raw dark frame. So that's another way to get those values. And this is a rather compute intensive operation. So we'll
Looks like it's doing your laundry. You're on cycle spin.
Yeah, it's on the spin cycle. It's going to do it 8 times even. The laundry's almost done. All right. So we don't want to take it on faith that it's something good. Let's actually evaluate it visually. Let's click on dismiss here to get rid of that dialog and zoom into our background. It does look better than what I remember it looking like before. If you want to be sure, we can just go to, looks like I got some hot pixels in there too. My dark frames were probably out of date there. But you can go to view image undo or control Z and see what it looked like before and do a redo. And you can see, it applied a fair amount of noise reduction there, but it wasn't over the top. I'm not seeing those checkerboard patterns I was talking about. So I think that's just about right. So yay, I'm happy with that. And I'm just using the scroll wheel here on the mouse button to zoom in and out, by the way. All right, let's do the same thing for oxygen and sulfur, and I will take those on faith. So we'll go to script again, noise reduction, mirror denoise. And we selected 03. We're going to select the matching flat, kick that off. Doo-doo-doo. It might feel like this is taking forever, but things pick up a lot after this step, guys. So it's gonna, I do think we'll be done by 9. And if we keep an eye on that frame there, we should see it change very slightly in the background. All right, it's subtle, but you know, it did good things. Let's finally do it to S2. Again, select the matching dark, or flat rather. And we'll denoise that as well. And we're done. All right, dismiss. All right, next thing we're going to do is cropping. So you can see we got some like junk around the edges here where, you know, the alignment was a little bit off. You know, it's never going to be perfect. So let's start by figuring out which frame has the most junk around the edges. So it's a lot there. Hydrogen alpha is actually remarkably clean. S2 also pretty clean. So O3 looks like it has the most cropping required. So let's work with that one. We need to crop each one of these frames the same exact way, or else we can't combine them later on. So we have to make sure that we all crop them the exact same way. And to do that, we're going to use this dynamic crop process. First of all, we're done with these flats, so we may as well get rid of them. And let's click on dynamic crop. Just double click that. Now, as I said, PixInsight's user interface is weird, and it doesn't get much weirder than dynamic crop. So let's start first of all by sort of zooming out a little bit so we can actually see the edges here and manipulate them. What I'm going to do is kind of manipulate my mouse until it looks like that, where I have that little icon suggesting that I'm going to crop in from the right. I'm going to just drag that in a few pixels to make sure that I don't have any of that noise around the edge there. And, you know, it looks like there might be a little bit on the bottom too, so I'm going to bring that up a little bit too. And even though I don't see anything on the left and top, I'd rather be safe than sorry. We may as well go ahead and pull that in a little bit, just in case, because there's nothing out there I really care about losing anyway. Now, if you were going to be thinking about image composition at this point, you could, you know, and apply whatever cropping you think will look good visually. I like to do that as sort of a last step when I'm in Photoshop, but, you know, to each their own. Now, you would think I could just, you know, press the check marker and something and be done. No, don't do that yet. It gets weird, guys. So we're going to grab this little triangle icon, okay? And we're going to click and drag that out to the desktop. And what that does is create a copy of this process that I can then apply to these other frames. But first, I need to apply this process to this frame. So I need to click on that checkbox, and that will crop my O3 image. And then I want to actually stop running this process on this window. And to do that, I need to click the X button. Otherwise, it will complain later on. All right, and now what I need to do is select my other frames. Let's start with S2, and I'm going to drag this process icon onto the S2 frame, and that will crop that in the identical manner to O3. I'll select my HA frame and drag that process onto there as well. All right.
You're right.
Weird.
That's pretty dang intuitive.
Yeah, I have to have a cheat sheet for this myself to this day. Hey, Richard, I didn't even know you were here. Thanks for watching, Richard. We'll have a recording up if you want to see the fun ending to it. And yeah, if you guys like want a good cheat sheet, let me grab a book. Kind of the Bible is Warren Keller's Inside PixInsight. So you know, a lot of these recipes that I'm showing you have their genesis in this book, and it's a great reference for all these weirdisms of PixInsight. There's also a new one. This book just came out last week. It's called Mastering PixInsight. I really like it. It's a beautiful book. It's actually a pair of books. One's kind of a tutorial, and the other one's kind of a reference for PixInsight itself. So this is awesome too, guys. Because yeah, this stuff is hard to remember. All right, so we're done with that process. Let's go ahead and right-click on that and delete it. Whoop. Moving on. Next thing we're going to do is background extraction. So it doesn't look too
If
bad.
I might ask,
Yeah.
why don't you combine the three and then do the cropping?
Because I want to apply background extraction to each one individually, which is what we're about to do. So
Okay.
you could do it
Does
that
that
way.
require the cropping to be done before that?
Technically, no.
All I'm saying is, could it be done later on after they've been combined to make a color image, rather than trying to go through this copying the dynamic crop to each of the other two?
So you probably don't want to do that because background extraction will get harder than it has to be. So if you have a bunch of junk around the edges, it's going to be hard for the background extraction algorithms to work properly. So that's kind of the main reason that we're doing this as one of our first steps.
Okay.
Excuse me. So let's do some background extraction. So the idea of background extraction is to like kind of remove any gradients in your image that might be due to light pollution or whatever. It actually doesn't look too bad here. You know, you could make an argument that I don't need to do any, but yeah, we should. So kind of the easy way of doing it is automatic background extraction. If you double click on ABE, it will show you my little cheat sheet of settings here that usually work well. The thing though with automatic background extraction is that it usually doesn't work real well on nebulas because you have, you know, you don't have a whole lot of like empty dark space there for the algorithm to work with. It doesn't really know where the nebula is and where the darkness of space is. So it tends to like try to calibrate out parts of the nebula itself. But, you know, we can try it. It's always going to be a lot easier to use this if you can get away with it. So let's go ahead and just try to apply this to this image. Now, the way, again, the UI works is you're going to select the window that you want to operate on, and then click on the square. What else would you click on to make it go? That actually applies this to that image. Boop. And it looks terrible, but we're just going to restretch it again. So down to your screen transfer function, we're going to restretch that. We're going to click on the radioactive button and see what it did. And you can see it did terrible things. So like I said, nebulas confuse it. It actually made things worse. It actually gave us this like weird like brightness on the corners here that isn't real. I don't like it. So let's go ahead and undo that. Image, undo. And we'll apply that stretch again with the radioactive icon. So ABE, automatic background extractor, isn't going to cut it for this image. We're going to have to use something called dynamic background extraction, where you actually place those points by hand that tell it what should be dark and what shouldn't. So I'm going to go to the process menu. I'll go to all processes. I'm going to select dynamic background extraction. All right, so let's start with the HA data here. I'm going to click on that. And you see I have this cross here. That means that I'm applying the dynamic background extraction process to this image now. And what I'm going to do is try to click a few points in parts of the image where there is no nebulosity and no star. So I'm going to try to select some points that represent the blackness of space that we'll use to calibrate the background. So how about here and here and here? Get a few that are close to the edge. Get a few that are kind of more toward the center if you can, but you want to make sure you're not clicking in any spaces that have nebulosity, if you can help it. And you just kind of have to eyeball it. All right, so that's probably good enough. You don't want to have too many or else you end up overfitting things. You know, typically real gradients are going to be pretty simple in nature. So you don't want to have too many points here, but let's go with that. All right, if we open up target image correction, we're going to set that to subtraction. So generally, you're going to use subtraction if what you're correcting for is light pollution, and division if it's vignetting. In this case, it's light pollution primarily because that's my main problem. We're going to replace the target image with the result of this operation. And kind of like with dynamic crop, I'm going to drag out a copy of this process for use on the other two images. So I have to do that all over again. And I can actually apply this in the same way. So before we do anything, I'm going to grab that triangle and drag that out to the desktop. And that will allow me to apply that to the other two images if I like what it did. So let's take a look at what it does. I'm going to click the green check mark. Why it's a check mark and not a square anymore? Because this is a process and not a something else. It's a dynamic process, I'm sorry. Execute. All right, so we have two things. This is the background model that it came up with. So let's go ahead and stretch that. And that's kind of the gradient that it figured out based on those points. It's weird, but looks reasonable-ish. Let's close that out and actually see what it did to the image itself and make sure it looks okay. I'm going to stretch that again. It looks pretty good. I don't see any weird stuff around the edges like we did before. So I'm actually pretty happy with that. So let's go with that. So again, just like in dynamic crop, I can X out of that and just drag that process to the other two to do the same thing to them. Boop. It should give me a very similar background model. And let's stretch that again. So there's my corrected S2 image. And again, I'll drag that to the O3 as well. And stretch that. All right. A little bit of funky stuff going on there on O3, but it's really the HA that we care about the most, and I'll explain why shortly. All right, where are we at? So we're going to put aside our O3 and our S2 for now and focus on our hydrogen alpha. The reason is we're going to take this hydrogen alpha data and have it double as our luminance data. So we're going to kind of use an approach where we're going to take our best data here, which is our HA data. You can see that's really, really clean. And we're going to use that to define where the details in our image are. And we're only going to use the data from the other two filters to provide color information to this image. All right, so it's kind of a way of cheating and making sure that we're not getting that really noisy sulfur 2 and oxygen 3 data and carrying that noise over into our final image. We're just going to use that for color data and nothing else. So what we want to do is focus on this hydrogen alpha data and try to make it as clean and sharp as possible. That's our objective next. To do that, we'll need a couple of tools. One is going to be a luminance mask, and that will allow us to mask out this image so that for things like noise reduction, we're only applying it to space and not to the nebula itself where there's more signal. Or if we're sharpening, we don't want to sharpen the noise in the background, we want to sharpen the nebula itself. So that luminance mask will come in handy for that. So to do that, grab this HA identifier and drag it over somewhere over here. What that will do is create a clone of the image. So first of all, let's give that a new name. I'm going to left click on that and we'll call it lum_mask. However, this is still in linear space and it's not really helpful as a mask because it's not really aggressive enough. So the first thing we're going to do is bring this into non-linear space. We're going to stretch it. And to do that, I'm going to cheat with one of those scripts that I had you download ahead of time. We're going to go to Script, Utilities, Delinear. All right, so now we're no longer in linear space, and you can tell because if I actually reset the screen transfer function to do nothing, it still looks like something. So I don't have to stretch it anymore. Now I want to actually exaggerate that a little bit more. So I'm going to click on the curves process icon here. Again, PixInsight is weird. What we want to do is actually preview what this will do before we apply it to the image. And it turns out that to preview something in PixInsight, you click on the open circle icon. What else would it be? So let's go ahead and click on that circle, and that will give me a real-time preview of the curve that I'm going to apply. So what I want to do is kind of make a mask that will have a really bright area around the nebula itself and the stars and keep the background of space dark. And this is actually pretty close, but I can manipulate this curve by just grabbing the control point and playing with it. Make sure that space looks black so that I apply as much noise reduction as possible out there, and make sure the nebula itself is nice and bright so that any sharpening I apply to it will be applied aggressively. That looks about right. So I'm going to click on the square icon to apply that to my image. You get used to it after a while, I promise. And now I have a nice shiny new luminance mask. All right, let's tuck that away for now. I'm just going to roll that up. We also need a star mask. That's going to be useful for when we're doing deconvolution. So similar process there. I'm going to grab my HA image, drag it over here to make a clone. Again, I'm going to delinear it under Script, Utilities, delinear. And I'm going to cheat. Making star masks is a kind of a tedious process, but I have a script that makes it easier. Just go to Script, Utilities, ADV star mask, and it will just magically make one for you. Looks reasonable. Now, there are edge cases where you have like a super really bright fat star in there, where sometimes you have to have like two different star masks, one for big stars, one for little stars, but they're all, more or less the same size in this image. So we got lucky. We can just use that. So let's go ahead and rename that. Double click on the tab there and we'll call it star_mask. And we'll roll that up as well. We're done with this clone here. We're not going to use it. Just close that out. Yes, close it anyway. All right, so now we have our hydrogen alpha image, we have a luminance mask, and we have a star mask. Next thing we want to do is deconvolve this image, which is basically going to sharpen it up a little bit. So the strategy now is to actually analyze the shapes of the stars in this image. They're not perfect circles. And that will tell us a little bit about the point spread function of this image, basically how the actual light has been spread out to its neighboring pixels. And we're going to try to correct for that. And this can be a pretty good way to sharpen things up. Technically, it's not sharpening. It's actually trying to deconvolve, which is, well, more of a principled way of sharpening, I guess, is a way of thinking of it. But first, we need that point spread function to feed into the algorithm. So the next step, again, we're going to cheat. This used to be a hard thing to do. No longer hard. Go to Script, Render, Psf Image. Make sure you have the HA image selected before you do this. It's a very common error to have the wrong image selected and apply a process to the wrong image inadvertently. So just be aware of that. We're going to click on Evaluate. And this will evaluate the stars on my image automatically. And there's our point spread function. So you can see it's not like a perfect circle, but it is capturing kind of like how that light is spread out along neighboring pixels, and we can correct for that. Now to actually create our PSF image, we're going to click on the Create button. And now we have a new PSF image down here at the bottom. So let's go ahead and close out of this. And there's our PSF. We can get rid of this process that we use for dynamic background extraction, just to clean things up. All right, so now we have everything we need to deconvolve. We have a luminance mask, we have a star mask, and we have a point spread function. So again, you don't want to be sharpening noise, right? So we want to mask out that background as a first step. So I'm going to open up this luminance mask, just double click on it. And to apply this mask to this image, I'm going to grab that luminance mask identifier and drag it over to the left kind of column here of the window here, if that makes sense. And that will apply that as a mask to the image. So basically, all the red stuff is masked out. So the operation I'm about to do, the deconvolution, the sharpening, will only be applied to the non-red parts of the image. So that's what we want, right? Like, we want to like sharpen up our stars a little bit. We want to sharpen up these details in the clouds of the nebula. That's exactly right. Let's double click on decon for my process icon set. So we've already selected our view identifier. That's the PSF image that we already made. Make sure this is set to external PSF. You want to do about 30 to 40 iterations typically. De-ringing is going to avoid artifacts where you end up with dark rings around your stars due to deconvolution. And you want to make sure the global dark is set to like 0.01. That's usually about right for my images anyway. You want to do local de-ringing and give it the star mask that we created. You can actually select that there with this icon here if you need to. And that will allow it to actually apply the de-ringing just to the stars. I've also baked in some further sharpening here with this wavelet regularization settings here. That's all just kind of like stock settings that I just stole from that PixInsight book actually. Make sure that that image is selected, that you want to apply the deconvolution to, and we will click on the square to apply it. Boop. And this is a rather intensive operation, but it should be done in a minute or two. All right, so let's just make sure it didn't do anything terrible. So I'm going to go ahead and unapply that mask. I'm just going to right click on the image, go to mask, and say remove mask. And what we're looking for primarily is dark rings around the stars to make sure that the de-ringing actually worked. That's going to be the main artifact that you would have from this, if anything. But I don't see that, so I think we're in good shape. Cool. And you'll see also that things look pretty tight. You know, we got some nice little sharp edges there around those clouds of gas there, so that's cool. All right, so deconvolution is done. So at this point, we have a nice clean hydrogen alpha image here, and that's going to double as our luminance data as well. Let's roll up that luminance mask, just get out of the way. Now comes the fun part. This is where we become artists and we kind of decide what our color scheme is going to be. So it's time to finally combine our hydrogen, oxygen, and sulfur data into a color image. Now, if this were broadband imaging, if we're doing like a galaxy or a globular cluster, this would be a pretty straightforward thing to do. You know, we would just want to like calibrate things to be true color, right? But it's narrowband, so we have a little bit more artistic license here to work with. There's more than one way to do it. So you kind of have to start by thinking about what your goal is for the image. Do you want to try to represent what this thing looks like to the eye if you had, you know, bionic vision that could actually see things as faint as a nebula? Or do you want to make something that is representing the ratios of the different types of gases in this image? Do you just want to make a pretty picture? That's okay. But, you know, you got to kind of start with one of those. I'll show you all three. So let's say that I want to represent this kind of like what it would look like to the eye. Now to do that, I'm just going to keep everything as is as far as their actual levels of data. So I don't want to rescale anything. I want to preserve the actual amount of sulfur, oxygen, and hydrogen that was picked up by the sensor, which means it's going to be really dominated by hydrogen. So I'm going to expect to see kind of a red image if I'm going this route. Now I do have kind of a secret formula that I cooked up myself of how narrowband data maps to different visible wavelengths and combine them together. So if you double click on PixMath NV here, this allows you to combine the color channels into whatever way you can dream up, basically, to produce a color image. So my secret formula for trying to make something that looks realistic is as follows. I have a little cheat sheet of my own to the left here that you're not seeing. So one way is to assign the red channel to half of hydrogen alpha and half of sulfur 2. I'm going to assign the green channel to 0.695 times O3 and actually 0.094 times hydrogen alpha. This is actually taking into account that there's actually some hydrogen beta in the hydrogen alpha data that I collected. And for the blue channel, I'm going to set that to 0.411 times oxygen 3 and 0.1 of hydrogen alpha. So there is kind of a scientific basis to this. You know, if you're trying to recreate synthetic RGB data from narrowband data, this is the most accurate way of doing it that I've been able to cook up. Obviously, it's never going to be perfect, but it's pretty darn close. So to apply this, I'm just double checking my values here. We're going to select the HA image here and click on the square to apply PixMath to that and the other frames. And it should create a new image here. We do need to stretch it. So let's click on the radioactive button. All right, so things are kind of green. So I'm going to actually de-link it. If you click on this little chain icon here, it will automatically try to balance the color for you when you do it again. So that's, you know, sort of kind of what you'd expect to see when you're done in terms of color. So if your goal is to recreate what the Pac-Man nebula really looks like, this is reasonable. After further processing, it would look more red and realistic, but this is kind of like giving you an inclination of where you're heading. However, I don't think that's very pretty. I think it's kind of boring. So I'm going to get rid of it. Let me click back the link icon here before I forget. And I'm just going to discard this thing because I don't like it. Another common combination is the Hubble Palette, of course. And for that, we don't need pixel math at all. But we do need to scale our data. So if we're not actually going to try to recreate the real look of this thing, we can try to scale things up so that these different gases are more visible relative to each other. And the trick there is to use this linear fit process icon, which is basically going to scale your data to be comparable in each channel. Now, some people will say you should use as your reference the strongest channel. Some people should say the weakest. I believe the correct answer is the weakest. And for me, that will be sulfur 2. So let's take sulfur 2 as our reference. And I'm going to take the triangle and drag that over to HA. So that will basically scale the HA to be about the same level as sulfur 2. And I'll do the same thing for oxygen 3. Again, dragging the triangle over to it to apply that process to the oxygen 3 data. All right, so now everything's kind of apples and apples. And let's go ahead and rescale that just so it looks pretty. Make sure we didn't lose anything in the process. You know, if you're dealing with like really faint stuff, sometimes you can get into weird quantization artifacts here, but things still look pretty clean to me. All right, so we don't need pixel math for something like as simple as the Hubble Palette. We can just go to RGB Combine. So let's open up RGB Combine. We're going to map our red channel to sulfur, S2. We're going to map green to hydrogen, HA, and we'll map blue to oxygen, O3. So the Hubble Palette is SHO. That's how it works. And for channel combination, PixInsight is weird. We're going to click on the filled in circle icon this time because it's applying a global process and not applying it to a specific image. All right, and again, we'll have to stretch that out to see something. Oh, that's looking more interesting. And since we balanced everything already, it shouldn't really matter. Oh God, no, balance it. So make sure that balance icon is on. So this is what your typical Hubble Palette image will end up looking like. On the plus side, it looks like a Hubble image. You know, it's got that kind of weird, weird puke color there for the hydrogen, but it has some pretty blues and greens in there too. The bad thing about SHO, the Hubble Palette, is that your stars always end up being magenta, which sucks. I hate that. There are ways around this. One way is to actually shoot RGB data just for the stars, subtract out the stars for the image, and add in the RGB stars. That's really hard. That's probably the subject for a whole other workshop. Or you can cheat. Go to the script menu, and I think it's under utilities. I don't usually do this. It's got to be under here somewhere. There is a script for cleaning up magenta stars. Render? No. Maybe it's under process. I'm pretty sure it's under script. Hang on. Why am I not seeing it? Does anyone see the word magenta? There it is. Correct magenta stars. And we'll just say fine, go. And you can see it actually did a decent job. The stars look okay. You know, I don't think they look terribly realistic, to be honest, but they're a heck of a lot better than that magenta garbage we had before. So if you want a really quick and dirty way of making your Hubble Palette stars look better, that's one way to do it. This isn't bad. You know, I'm going to keep this around. That's a contender. I could live with that. So I'm going to rename this to Hubble. But I have other secret recipes that I can try too. So we've seen what we get if we try to like recreate what this really looks like to the eye. We've seen what we get if we try to like recreate scientific data in the Hubble Palette. But I just want a pretty picture. You know, I'm shallow. I'm sorry. So I have some other secret formulas here. Let's try one that I call natural. So I'm going to close out channel combination, open up PixMath NB. And for this secret formula, oh, thanks for coming, Laura. We're going to say point for red. We'll set that to 0.76 times hydrogen alpha and 0.24 times sulfur. We're going to set green to just O3. And we'll set blue to 85% O3 and 15% HA. So let's select like the HA. One of those input frames has to be selected, and we'll click on the square. See what we get. Let's stretch that. I think that's pretty cool. So it's kind of pretty. You know, we got this like, you know, kind of neat blue center here, some like natural looking red hydrogen around it. And the star colors look okay-ish. They're not awesome, but some look a little bit red and some look a little bit blue, which I think is a better representation of reality. So I'm liking that. Yeah, let's call that natural. So which one do I like more? Gosh. You know, just for the star colors alone and the lack of that kind of weird puce thing, I think I'm liking the natural color image in myself personally. Again, this is like just an arbitrary blend that looks good. Um, but you know, you're still getting some scientific value there. The different types of gases do influence the what you're seeing there. So again, it depends on your goals, but I think that's pretty cool. So let's develop that further, shall we? All right, so again, we're just going to use this for the color information, and we're going to use the hydrogen alpha image for the actual detail of the image itself. But I still don't want to pick up a whole bunch of like color noise in there. You can see it's still pretty grainy in there. So I'm going to apply some pretty aggressive noise reduction. But first, I'm going to do some background correction to this. Let's go ahead and run ABE on it. I know I told you ABE on a nebula is bad, but at this point in the process, it's fine. Don't worry about it. Apply that. Stretch it again. And we're also going to use the SCNR process here. What that's going to do is cut out some of our green noise. All right, so you can see that the background looks a lot more natural now. There is some weird vignetting going on because I used automatic background extraction, but it doesn't matter because I'm using my nice clean hydrogen alpha data for the detail of the image itself, for the luminosity. So I can get away with that. I cheated. All right, so let's denoise this pretty aggressively because I want nice, clean, smooth color data. And I'm going to use the HA for the detail so I can get away with smoothing this out more. Alrighty then. So to do that, we are going to, normally I have enough satisfaction from your denoise that I don't do this step, so it's not in my process icons, but we'll have to do this the hard way. We're going to go to multi-scale linear transform under processes, which is a fancy way of saying noise reduction. Now, again, we don't want to do too much. Well, actually, so normally when you do noise reduction, you want to mask your image so that you're only applying the noise reduction to the background. But in this case, I actually want to do it to the whole thing because I want to smooth out that color data that's being applied to the luminance. So as you'll see later, you know, you can mask things out to only apply noise reduction where you want it. But in this case, I'm going to actually apply it to the entire image. So let's set the layers to 5. Again, this is kind of a set of cheat values that I got from that Warren Keller book. We're going to double click on layer 1, select noise reduction, set that to 5 with an amount of 0.5 and 2 iterations. We'll set layer 2, activate noise reduction, set that to 3. The amount will be 0.45, iterations 2. For layer 3, we'll set that to 2.5, amount 0.4, iterations 2. For layer 4, 1.5, 0.4 and 2. And if you were with me for the planetary imaging, this is very much analogous to the wavelets that we applied there, but it's kind of like in reverse because we're using it to do noise reduction instead of sharpening. So for the last one, we're going to say 0.5, 0.4, and 2, and we'll leave R empty. Make sure the target is set to RGB, and we'll go ahead and apply that to the image. Boop. Eric, am I entering those values from experience? No, I stole them from this book, and they've worked for me pretty well. But from experience, I know they work well. And if we zoom in, we can see that data is a lot cleaner. That made a huge difference. Yeah, so I'm digging that. This looks like really nice, smooth color data, which is what I want, because the detail is going to come from someplace else. All I care about here is the color. Very cool. All right. So where are we? Next, we're actually going to stretch things out. So we finally, we're done in the linear space. It's time to actually stretch this to the non-linear space before we start doing color combination. So we're kind of done with O3 and S2 right now. We're just going to be focusing on HA and the RGB data here. We need to stretch these out in the same way, basically. So let's try to figure out what we want this to really look like. So if I hit the radioactive button there, it kind of has like, you know, a default setting, but it's kind of too bright. You know, there's a little bit too much noise, too much brightness in the background here. So let's play with that. What I'm going to do is hold down the Control key and hit the radioactive icon. Because again, PixInsight is super intuitive. If you hit Control key and hit the radioactive button, of course, you will get this dialog here. So what I want to do is reduce the target background. This will basically make the background darker. So let's try making that like 0.16-ish. And let's just go ahead and hit OK and see what it does. See, I think that looks more reasonable. That looks more like a good looking photo to me. So let's go with that. We can always adjust it later on. So that's good enough. All right, so there's a bunch of different ways in PixInsight to stretch your data, and it's going to depend on whether you have like a really bright galaxy or something else. But for something as straightforward as a nebula, you can get away with just like applying this very same stretch that we're using in screen transfer function to the final image. So to do that, there's a little trick here. Open up histogram transform, that process, and, oh, this gets weird. What you want to do is grab the triangle from screen transfer function after you've applied that and made it look good for that image, and drag that triangle to the bottom row thing here of the histogram transformation window. And now if you hit the apply button, the square, that will apply that very same transform to there. Now it's going to look white because I stretched it and I'm still stretching it again. So to see what I ended up with, I'm going to click on the reset button on screen transfer function, and that will reveal the image unstretched. Okay? That was weird, but that's how it works. I'm going to do it again to the RGB data. So I'm going to select my RGB data, which is called natural. I'm going to reset my histogram transform and do the same thing. So I'm going to hit the radioactive button here, apply the same stretch to that color data, and I'm going to drag that triangle up to the bottom row of histogram transformation, hit the square, and then reset the screen transfer function. All right. Now we are finally ready to do our luminance combination with the RGB data, which is pretty easy. Now you can make this complicated if you want to. Some people like to extract the luminance channel from the RGB data and make sure that everything lines up perfectly. But if you were careful in applying the same stretch to both the luminance and RGB data, it'll be good enough. So double click on LRGB. And we're going to select what we're using for our luminance channel. So I'm going to select the hydrogen alpha image as my luminance. And now I just drag that process, drag the triangle to the RGB data. Oh yeah, this is starting to look good. I'm digging that. All right, we're getting toward a finished image here pretty quickly. All right, so now we just kind of do some final tweaks here. We can do a little bit more noise reduction if we want to. So, it's still kind of grainy in space there. And yeah, it kind of looks like my dark frames. I probably should have had a more current set of dark frames because I am seeing some hot pixels in here. That's bad. Another way to deal with that would be through a process called Cosmetic Correction, which I did not do during the pre-processing step. But you'll see some process icons for that here if you want to play with that. Coscore NB. Oh, well, it doesn't work because that dark file's not there anymore. But that's another way to address that stuff if you see it. But we'll live with it for now. All right, let's do some noise reduction. So I'm going to show you how to use a Luminance Mask for that. Let's open up our Luminance Mask. Drag that over to the left pane of our image here that we want to reduce the noise on. And in this case, I want to mask out the inverse of this, right? Because I want to be applying my noise reduction to the background, not the foreground. So I'm going to right click, go to Mask and say Invert Mask. So now I'm masking out the nebula itself, applying the noise reduction to the background of space. So let's double click TGVD, which is a denoise algorithm that works well in the nonlinear space. These presets should work well for you. And let's just click the square icon to apply it. All right, and we've applied the noise reduction just to the background there. So let's zoom in. Make sure it looks better and not worse. I think it does. That's good. And one more thing we can do is sharpen up the nebula a little bit further, get those little clouds of gas to pop a little bit more. So for that, I'm going to invert the mask again, back to make it normal, because I want to apply the sharpening just to these clouds in the nebula itself and not to the noise in the background. And for that sharpening operation, technically it's not sharpening, it's local contrast enhancement is what I'm doing. So open up local contrast, and this will just kind of like boost the contrast between those edges. And, you can play with the contrast limit and the amount sliders if you want to be more aggressive, but really less is more here. So this is kind of a conservative setting here that isn't going to do a whole lot, but it will make it just look a little bit better. So let's go ahead and apply that. All right, so it's hard to see, but it did make those clouds pop a little bit more. Let's get rid of our mask. Actually, let's leave the mask on. What I want to do now is punch up the color a little bit. So let's hide the mask. So we'll go to mask and say show mask. So now the mask is still applied, but you just don't see it. So I'm going to click on curves 2 here. And what I want to do is actually bump up the color saturation. And because I still have that mask applied, I can just saturate the nebula itself and the stars without saturating the noise in the background, right? So to do that, again, I'm going to click on this open circle to preview what I'm doing. And I'm going to click on S here. That means what I'm going to be stretching is the saturation of colors and not the pixel values themselves. I'm just going to stretch the color. So let's grab the middle of this line somewhere and drag it up. And we're trying to make those star colors and the nebula colors pop a little bit more, but you don't want to go too crazy and make it look silly, right? So kind of got to use your eyeball here. There's a little bit of art to it. Right about there, I think looks pretty cool. So let's go ahead and apply that with the square. All right, let's remove that mask. See if we're happy with it. I'm digging how the nebula looks. I think the stars could have a little bit more color maybe. I don't know. I guess some of them are pretty blue. Let's go with it. Another trick you could do is just apply the star mask that we made earlier. Thusly. Let's show that. And by doing that, we could just like boost the color of the stars and nothing else, which is kind of cool. I will unshow it. Again, go to curves, preview it, kind of give the stars a little bit more of a boost. I don't know. Probably not worth doing, honestly, because it's starting to make some of them look kind of like a silly shade of blue. So I'm actually going to cancel this out and not do it. All right, let's get rid of that mask. And at this point, we're pretty close to having a finished image. So I'm done with PixInsight at this point. I'm going to take this into Photoshop and kind of give it its last looks. You could, continue finishing this in PixInsight if you wanted to. Basically, I'm going to adjust the stretch a little bit more to make the background more dark. And I'm probably going to end up cropping out a little bit of vignetting going on there in the corners there and frame the thing a little bit better. But I prefer Photoshop for those operations. So let's save this to a TIFF file so I can load it to Photoshop. So I make sure that I have that image selected, File, Save As, select TIFF, and let's save it in the root folder of our Pac-Man CFast folder here. And I'll just call it Pac-Man. You want to make sure it's 16-bit because for some reason, Photoshop, even in this day and age, cannot handle 32-bit TIFFs properly. I don't know why, but it can. But everything's stretched already, so it's not that big of a deal. All right. And if you want to save this session in PixInsight, so if you did want to come back later and kind of like try different things, we can do that too. By the way, let me just point out the History Explorer. Oh, the project, where is it? Why don't I see it? Never mind. Anyway, there is a view here that actually looks at the history of any given image, where you can actually like roll things back and like start over if you want to. So that's kind of a cool thing in PixInsight. But if you did want to like revisit this later, we can just say File, Save Project, and click on the folder icon there to tell it where you want to save it. which probably is not automatically set to something that makes sense. Pac-Man Cephas. And we'll just call it Pac-Man.pxi project. Okay. And that will go out and write all of those different windows out automatically and their entire history as well. So if you want to come back and fiddle with things later on, which you often do, you can just load this project up and fiddle with it some more later on. And it's a lot of data, so it takes some time to write out. All right. Well, there it is. If you like Load History Explorer by right-clicking on the image, I can actually look at the history of everything I've done to this image and roll it back and try different things. So that's kind of cool. Like I can go back to any point of the processing of this natural image here and say, I want to try a different approach or try different settings, right? So if you did want to come back and revisit things, that's how you would do it. So I've saved off everything in PixInsight. I can safely close this out now and load up Photoshop and just kind of apply some final tweaks to my image. So let's go ahead and open Pac-Man Cephas, pacman.tiff. All right, let's fit on screen. So, the first thing I want to do is adjust the stretching a little bit. I think the background's a little bit too bright. One way of doing that is going to Image Adjustments Curves. But often, you can see it's definitely, there's definitely some stuff we can cut out there. But a lot of times you just go to Image Auto Contrast. It just kind of automatically does the right thing. And yeah, that's not bad. Could go a little bit more. I'm going to undo that. Let's actually do it by hand. So adjustments, curves, or you could do exposure as well. Let's kind of like try to cut out that garbage there we don't need. So that's cutting down the background, boost up the foreground a little bit. Right about there looks good, I think. Another thing that often works well is auto color. Just see what it does. If you don't like it, you can always undo it. I like that. I like that a lot. That looks good. Cool. Now we still have some vignetting going on here in the corners that are bothering me. So I want to crop this out. So let's go ahead and just select the part that I want to keep. Try to get rid of those artifacts. And you want to think about framing it. Rule of thirds and all that, but I just don't have enough stuff to work with here to apply the rule of thirds. So I'm just going to try to center it as best as I can. I'm kind of trying to get those kind of interesting stars there in the frame though. So let's select that as our frame and go to Image Crop. All right. We could try to like saturate things further, maybe. I don't think it really needs it, but if you wanted to, that's a pretty common thing to do too. You could go to Adjustments, Hue Saturation, bump up the saturation a little maybe. God, that looks terrible. I'm just going to leave that the way it is. Another thing you can do is apply some more sharpening to it. So we could go to Sharpen, Smart Sharpen, kind of play around with it. The way I like to do it here is like crank the amount all the way up to get a sense of like what the radius is actually doing. Let's get some clouds there. And, try to find a setting where it's not doing completely terrible things. Usually that's going to be about 1.5 pixels or so. And cut that down. Yeah, that's actually worth doing, I think. It's probably a little bit too much. Again, you don't want to be too heavy-handed on any of this stuff. Let's just go with that. All right, and yeah, we pretty much have a finished image here. Cool, guys. All right, so there is my Pac-Man nebula. We can save this. Probably want to save it as a different file name so that we can get back to the original one that we exported from PixInsight. We'll call this Pac-Man processed. Keep it as a TIFF if you want to like play around with the stretching a little bit more later on. And if you want to share it on the web with your friends, we can just go to File, Export PNG. Quick export is PNG. And that will give us a PNG file that we can upload to Facebook or Instagram or whatever your favorite social media watering hole is. Oh, Eric says rule of thirds. Oh, that's a photography thing. So basically for image composition, it's good to like split up your frame into thirds, you know, both horizontally and vertically, and try to get things that are focused on those third boundaries for some reason. See if I can find an example of that. So let's go to like my website here. So if you have, you know, enough details to work with, you can pull stuff off like that. You know, for example, in this image of the elephant's trunk, I tried to make sure that the focus of the trunk was like a third of the way over on the frame there. It just makes it more visually interesting. Same thing with the supernova photo if you blow it up, I believe. Like I made it a third of the way up on the screen there when I was choosing my cropping. So rule of thirds is a little bit of a trick for making something that's a little bit more visually interesting. Another little trick too, if you're doing galaxies, I may as well get a little bit of time here. Let me find a good example of that. You want to make sure that things look like they're lit from above and not below, given the choice. Let me see if I can find a good example. Yeah, for example, here in the elephant's trunk again, you can see that it kind of looks like it's being lit from this direction. And maybe it really is. Maybe there's a bright star there. But, you know, if you given the choice of presenting this image this way or upside down, you'd want to present it this way because it always looks better when you light things from above. It just looks more natural to your eye. If you're doing like a galaxy, that becomes a little bit more prominent. Let's look at this image of the deer lit group. You can see that I chose the orientation here so that it looked like this galaxy is brightest on the top. So little image composition trick for you there. But hey, we have an image. So we are done, guys. That is our finished processed image of the Pac-Man Nebula. It's been an hour and 45 minutes of work, but you know, when you're not talking about it as you're going, it can go a little bit quicker. But yeah, we made pretty good time on that. For a complicated situation where we actually had data collected over 2 different nights with 2 different sets of calibration frames, we made pretty good time. So if we have any final questions, I'm happy to take them. Otherwise, we can get on with our evenings. Anyone? Bueller?
Hey Frank, can you hear me?
Yeah.
Yes. For people who are like beginners,
Yeah.
In the amateur astronomy, what type of what would be the most basic telescope and also camera that I could use to take some dust pictures? Okay.
Well,
this is something, although I'm in a beginning stage, this is something that I would like to do one day. It's very interesting and very beautiful. So what would be the most affordable telescope and camera that I would be able to use?
well, it depends on your goals, right? So you can do things like the moon and planets and globular clusters with some pretty modest equipment. You know, pretty much, screwing a DSLR to the back of pretty much anything will get you that far. Although for planets, you want something with more of a long focal length. So, you know, a Schmidt-Cassegrain of some sort, like a Celestron 8SE or something along those lines. Most people, however, will tell you to start with a refractor. You know, something that's a little bit wider.
This one here, could I do something? This one is a Periscope 140 AZ.
So that looks like a reflector.
Yes, reflector.
Yeah, it's possible. I used a reflector for this image. It's just a bigger reflector. It's a 190 millimeter reflector with a camera attached to the focuser draw tube. So yeah, I do think you could probably get some good results with that. You know, I would definitely. Oh, Eric says, would you need a motor? Absolutely. Yeah, I couldn't tell if your mount was motorized there. It looks like it's not actually, so that
It's
would
not.
be an issue.
No.
Yeah, so if you're going to be doing long, thanks Eric for catching that. If you're going to be doing long exposure astrophotography, you need a mount that will track the object automatically. So for the scope you have, you'd want to be sticking to, you know, really short exposures where the rotation of the Earth isn't going to cause your image to be all smeary, right? So your scope is going to be well suited for taking quick snapshots of the moon. You know, maybe a quick snapshot of the planets, but, you know, they're going to look really small in that telescope, I think. But, you know, you'd get a decent image of the moon with that. If you want to do something more than that, though, you're going to need a mount that actually automatically tracks the sky. So, you know, you're getting into a little bit more money there, but it doesn't have to be crazy. You know, like a Celestron AVX would probably be more than enough for that telescope you have. And, you know, you could always just keep upgrading things as you go. I mean, that's how I got started. You know, I started off with a Celestron 8SE, which has had an Alt-Azimuth motorized mount, which is not ideal for astrophotography. But, you know, I got the feel of the process and how its stacking works, and took some, you know, okay-ish photos of like the Orion Nebula and the moon and like really bright targets. And later on, I moved up to a Celestron AVX mount, which is an equatorial mount that tracks a little bit better. And my images got a little bit better. Then I got a better telescope. And then after that, I got an even better mount, and I got an even better camera.
The camera? Any suggestion?
What's that?
What about the camera? Any suggestion?
Most people start with a DSLR. It might just be something you have sitting around, you know, like a Canon or something like that. And after that, kind of a next step for a lot of people is a CMOS cooled camera. Kind of like the ASI 294 MC Pro is what I started with in that front. And, you know, when you get totally immersed in it and you're like ready to fork over your paycheck, you can get a cool CCD camera like mine. This is actually taken with an Attic 383L Plus camera. So again, it's kind of like, you can kind of work your way up and just kind of like see how far you want to go. But a DSLR is a reasonable place to start. I mean, Derek in our club, you know, he's taken astronomy pictures of the day like on a routine basis, just using a cool DSLR camera. He's got like a little Canon, I forget what it is. It's not even a new Canon camera. So you can do a lot with a DSLR.
One of the 6Ds,
Yeah, that's right. It's a 6D.
the original.
Yeah.
Okay, that's good. Thank
All
you.
right. Glad to help. All right, guys. Well, I hope you learned a thing or two, or maybe I scared you away entirely. I'm not sure which, but that's what goes into processing an image like this in PixInsight. Again, we kind of like took the hard approach here where we had multiple nights of data. We had narrowband data to work with. So this is one of the more complicated scenarios you might be dealing with. But yeah, we got through it and we got a pretty picture. So yay us. And yeah, I think we'll do this again in January if you guys want to. If you have any specific topics you want to cover, bring it up with me. I'll put on my board member at large hat for CFIS. If you have any suggestions for the club, I'm your primary contact for that. So any guys, so thank you. Thanks you for spending the past couple of hours with us, and I will let you get back to your evenings, and I'll see you tomorrow night at our general meeting.
Thanks, Frank.
All right. Thank you. Bye, guys.
Thanks so much, Frank. Have a good night.
Have a good night.
That was incredible.
Thank you. Good night, guys.